Hey there, Physics 1. So today's plan is to talk a little bit more about standing waves on a string, and then I'll also look at a different scenario for standing waves where we have standing waves in a column of air, like an open-ended tube. So let's go back and talk about standing waves on a string. So a case where we have like a violin, perhaps, or a guitar, where you've got on either end of a fixed medium, where the medium is your string. You've got the string tied at one end, you've got the string tied at another, and your string can bounce up and down between two positions. You can generate standing waves in those sort of scenarios. So if we have a standing wave, we could generate different frequencies of standing waves. Frequency is going to be how quickly that wave pulse is vibrating, how often we are sending a wave down that string. And when we generate standing waves, our medium, which in this case is a string, is going to have a wave moving down from one end of the medium to another. It's going to hit the fixed barrier at the other end, and then it's going to reverse and travel back up the medium again. And we're going to get constructive and destructive interference within our system when that happens. Now, depending on the frequency we choose, we may generate a standing wave. A standing wave occurs when we have positions of constant complete interference, destructive, and complete constructive interference. So we'll get high points in the motion, and also we'll get spots on our medium where the medium does not appear to be moving whatsoever. We call those nodes. Where we have maximum amplitude, we have what we call an antinode. For a standing wave on a string, which means we have fixed ends, one guaranteed property of those fixed end systems is that we have a node at either end of our system. So if we're going to generate standing waves in a string that's fixed at either end, there's a few different ways that wave could look. What I want to talk about today to start us out is to think about what the wavelength would look like for a standing wave on a string. So I have here several different harmonics. This is our first harmonic, this is our second harmonic, this is our third harmonic, and this is our fourth harmonic. If you remember from the previous video, the harmonics are the possible standing waves that we can generate in our medium. Our harmonics, though, are always integer multiples of our fundamental frequency. So this first harmonic, that's our fundamental. If I know the frequency in hertz of my fundamental frequency, each of these harmonics is an integer multiple of that fundamental frequency. That's nice because it means if I know that my fundamental frequency is 25 hertz, I'm also going to get a standing wave on my string at 50 hertz, and one at 75 hertz, and one at 100 hertz. And that'll go on and on and on. There's not really I guess there's no, there may be practical limits, but there's no mathematical limit on our higher order harmonics. But let's take a look more closely at what this wave looks like. So if I have a, I'm going to focus on my first harmonic here, my first standing wave. Let's see if I can clear some of this stuff out of the way. And we'll focus on our first harmonic here, and that's this fundamental frequency. So let's think about how that relates to a full wave length. Notice I have a node, and I've got an antinode. I've got a node here. I've got a node here, and I've got an antinode. If I were to trace out this wave, let's think about it like that, that really only looks like half of a full wave. If you think about a wave, we're thinking about like a sine function or something like that, and it goes through a crest, and then back to a midpoint, and then through a trough, before we're back at the same point on the wave again. This distance is our wavelength, lambda. So if I look at this wave I've generated for my first harmonic, I'm actually only seeing half of a wave. If I want to have a full wavelength for my first harmonic, it's actually longer than the string itself. And so the first thing to note about our first harmonic is that the length of the string is only half of our wavelength itself. That's only half of a full wave. Now let's go and look at our second harmonic. I'm going to change colors here. So for our second harmonic, if I trace out what I see on this wave, I've got a node at one end, I've got a node at another, and I've also got a node in the middle. And when I trace out what a snapshot of this string motion would look like at any instant in time, now take a look at that. It looks like one full wave. And so for my second harmonic, the length of the string itself, the length of our medium that the wave is traveling through, is equal to the wavelength. Now, if I have my fundamental frequency here, okay, my integer multiple of the fundamental frequency, notice that the second harmonic should be twice my fundamental frequency. Like I said, if my fundamental frequency is 25 hertz, then in order to get the next highest frequency up, I'm going to double it. It's 50 hertz. But notice what's happened to my wavelength. My wavelength has changed at the same time. Remember, one of our fundamental equations here when dealing with waves is wave speed is equal to frequency times wavelength. Our wave speed is constant in this medium. So if my wavelength is going to double, my frequency must be half. Now, let's take a look at our third harmonic. If we're looking at our third harmonic here, let's see if I can find a wavelength. Well, one thing I know is I've got a node at each end. And now let's follow a snapshot of that string as it oscillates. There's half of a wave, and there's a full wave. That looks to me like it's roughly 2/3 of the full length of the string. So if I were to think about the entire length of the string, the length of the string is actually 3/2 of a wavelength. Because this is one wavelength, and I need to tack another little bit on the end, another half of a wave. So there's actually a couple different ways I can write this. Maybe I can rewrite this another way. So instead of saying that the length of the string is 3/2 of a wavelength, let's also write it in terms of what the wavelength is equal to. So another way to write this would be to say that our wavelength is equal to 2/3 of our total length of the string. It doesn't really matter which way you approach that, either one would work. And let's finally look at our fourth harmonic. Our fourth harmonic here, I've got my node at this end, I've got my node at this end, and let's take a look at how far I have to go before I get through one full wave. Got that bit. Now it looks like I've gone through one full wave motion. I've got from node to crest. Let's see, I'll do that in a different color for you. So I go from node to crest, back to node, down to a trough, and then back to a crest again. There is a wavelength. So if I think about the length of the string itself is 2 times a single wavelength. So I've got one wave and then a second wave to make up my full length of the string, L. Or I could say that my wavelength is equal to 1/2 of the length of the string. One important thing I'd like you to see here is that the length of the string is not the same as the length of the wave, but we can come up with a mathematical relationship. We can relate the two. And especially if we draw a picture of the standing wave on the string, we should be able to find that relationship between string length and wavelength of our wave. And also, if I know the fundamental frequency, I can figure out the frequency of any of our harmonics. All right. So, summary, I'm going to take a look here. So I'm showing our first harmonic, our second harmonic, our third harmonic, and our fourth harmonic. You can see with our first harmonic, when we have a fixed end wave, so we've got a node at each end and an antinode in the middle. Our second harmonic is going to be the wave that has 3 nodes and 2 antinodes. Our third harmonic has 4 nodes and 3 antinodes. And our fourth harmonic has 5 nodes and 4 antinodes. So again, I'd like you to see the patterns here, but I don't really want you to memorize these things. Because if I ask you, say, about the fifth harmonic and what that might look like, sure, you could memorize the number of nodes and antinodes in that mathematical pattern, but you can also draw it out. So if you know that you want the fifth harmonic, I know that I need to have an additional node in here. I need to have the next standing wave up. So hopefully it should look something like this. It's going to have 5 loops. And when I'm not drawing this in advance and having it, all done pretty evenly, you can see that my wave is not perfect. Hopefully that doesn't matter. Hopefully you guys are still okay with this. Let's see, I'll draw that as our second wave. Now, with this fifth harmonic, note how many nodes I have. 1, 2, 3, 4, 5, 6. 6 nodes. And then I've got these 5 points of maximum amplitude in my standing wave. 5 antinodes. And if I wanted to, I could come up with a relationship between the length of the string and the wavelength of that standing wave. I need to find one full standing wave. This is a half of a wave. That is a full wave. And if I think about each of these segments is 1/2 of a wave. And if I go across this length, notice I have 5 of those half wave segments. So if I think about the length of my full string here, I have 2/5 of that string when I'm making one wave. So I could write the equation this way for my wavelength of the string. The wavelength is equal to 2/5 of the full length of the string. Now, if I'm solving for L, I might rearrange this. So if I want to write the length of the string is equal, it's actually 5/2 of a wavelength. Depending on what you're solving for, you may want to write the equation one way or another, but notice that it comes directly from understanding what's happening in this picture and drawing the picture yourself. So at this point, we have looked at fixed end strings. And just as a reminder, if we want to change the number of nodes in our system, we do that by changing the frequency. If we change the frequency, the rate at which we're vibrating that string, we're going to see another thing change as well. Wavelength is also going to change. Notice that the higher the frequency goes, as our frequency goes up, our wavelength should go down. But the thing that stays constant in this system, wave speed. Wave speed equals frequency times wavelength, and wave speed depends on the medium. So assuming our medium is not changing, we're using the same string every single time, this value right here should be a constant. Oops. And if that's not changing, then I can use this mathematical relationship and understand the wave speed and how it relates to wavelength and frequency for any system of our harmonics. So I should be able to use that wave speed for any of my standing waves. Now, standing waves in a string is not the only type of standing waves that you could have. If anyone plays like any musical instruments, so a flute or a recorder, you get standing waves in those musical instruments even though there's no strings involved. So our next example is going to involve standing waves in an open-ended tube. So let's look at an open-ended tube. So when I say an open-ended tube, I mean it's open to atmosphere on both ends. So if I have a tube, for example, then I can have a maximum amplitude wave at one end and a maximum amplitude at the other. That means I have antinodes at the ends. The longest possible wave that I could generate in this system, where I have an antinode at one end and an antinode at another, is going to have a node right in the middle. It's going to oscillate from this antinode at one end, and maybe have a crest at one end, to a trough at the other. But one thing I want you to note is that is not a full wavelength. That's only half of a wave. If I want to generate a full wave, I need another half of that wave so I can get back up again to my crest. Our fundamental or first harmonic, when I have an open-ended tube, has one node in the middle, two antinodes at the end, but it's really only half of a wave. So the length of our tube is equal to half of a full wavelength. Or another way to write it is that our wavelength is twice the length of that tube itself. If I want to look at my second harmonic is going to be the next longest standing wave that I can generate in this tube. If it's going to be a standing wave in my open-ended tube, I need an antinode at one end and an antinode in another. If I have an antinode at one end and an antinode at this end, I can actually stick another antinode in the middle. And then I also have a node and a node because I have to cross through that center point. And so my standing wave for my second harmonic has an antinode at one end. It goes through the node to another antinode, another maximum vibration of my air molecules, back to a node, and then to another antinode. That's actually one full wave. So our second harmonic is the case where the length of the tube is equal to the wavelength of this standing wave. Notice in this, my my second harmonic, or my first overtone, I have 3 antinodes and 2 nodes. I can draw another wave. My next highest frequency, my third harmonic, is going to be the wave that's a little bit higher frequency, but also generates a standing wave in this tube. If I'm going to have a standing wave in this tube, I need to have a node at one end, an antinode at one end and an antinode at the other. Notice that each time I add another harmonic, I'm basically just sticking another half wave into the system and compressing everything a little bit. So this is my previous wave. I've compressed it, and I'm going to add another half wave onto it. So notice I have an antinode at one end and an antinode at another. Notice my wave now is at a crest at the left end and a trough at the right end. But this standing wave here, I draw by just taking my previous standing wave and adding another half wavelength and compressing it. And I need to add a half wavelength because I still need to have an antinode at the end. And if I'm going to have an antinode at the end, I can't add, a quarter or a third of a wave or something like that, because going from one antinode to another in my wave requires 1/2 of that wave. All right, so if I look at my third harmonic, I've got a node or an antinode at one end. I've got an antinode at the other end, but I also have 2 other antinodes that happen in this oscillation. And in terms of the number of nodes, where I have 0 oscillation, I have 3 points where I cross that middle. Notice that I'm using what you might look at as a transverse wave, basically as representing the oscillation of the molecules in this tube. Okay, I know it's drawn as a transverse wave, but this is representing how much the air molecules are in motion. So right here in the node, I have very little amplitude of oscillation for those molecules. At the ends of my tube, I have the maximum possible oscillation of those waves, and here as well. For my third harmonic, I have 3 nodes and 4 antinodes, and I can also come up with a nice, tidy relationship between the length of the tube and the wavelength. What I hope you've noticed is that there's very, very good similarity between the fixed end strings and the open-ended tubes. They basically behave the same way, except that we've swapped nodes and antinodes. In the open-ended tubes, where we have an air column vibrating, you get an antinode at the ends. For a string, the string works by having a fixed endpoint. You have two nodes at the end. But this relationship here for the length of the string and the wavelength, that works. So if we were to, you might notice that our pattern so far is that a wave is fixed in place if there's a node, so like the end of a string. So if I have a string, a wave on a vibrating string, a violin string or something like that, there is a node at each end. But a wave is able to move or oscillate if there's an antinode at the end. So in a tube, we have a column of air at the end. This is open, and this is open. And when we generate a standing wave, we get our maximum oscillation. We get an antinode at the ends of those tubes. There's another case, though, that we could look at. And this one is going to be kind of a combination of the other two, which is why I want to make sure we're clear on the wave on a string and the wave in an open tube, because our next case is going to be one where we are fixed at one end and able to move at another. Slightly more complicated case, but one that probably is pretty familiar. So I think my reference for these is usually like an organ pipe. So if you've ever seen like a big pipe organ, there's a tube and it's open at one end and it's closed at the other, which means that I don't get, if I've got air in this column, the air molecules right up against this surface can't move. If it's closed at one end and open at another, we're going to get a really different sort of standing wave pattern. And that's what we're going to look at next. All right, if we have a closed-ended pipe, let's zoom in here on our closed-ended pipe. We're going to think about a case where this pipe here, you see it, has a standing wave in it. If I'm looking for my first harmonic is going to be the one that is the longest wavelength or the lowest frequency that can generate a standing wave in this system. If I have a closed-ended pipe, I need to have a node at the closed end. The air molecules can't vibrate much there, but an antinode at the opposite end. So what would that wave look like? Well, that wave is going to be at a node here and an antinode here. The longest wave I can generate that looks like that is right there. Now, if I want to think about how much of a wave I've drawn, it's a smaller fraction than what we saw before. When I was looking at my waves on a string or my waves in an open-ended tube, my first harmonic was always half of a wave. This is not half of a wave. If I want it to be half a wave, I need to tack on a little bit more. But that's still not a full wave. I would need to draw another section. And then another. If we look at this, all I have here is 1/4 of a wave. For my closed-ended tube, my first harmonic is actually only 1/4 of the full wavelength. So the wave in that tube, if I wanted to get the wavelength of the corresponding wave, it's going to be 4 times the length of the full medium that's shown. So if I think about this system here, that tube is only 1/4 of the full wavelength. Now, if I want to think about the characteristics of this, counting the nodes and antinodes in the structure, I have one node at the left end, and I've got one antinode at the right end. And that's it. Now, if I want to think about what the next possible wave is that I could put into this system, I'm going to need to do some more drawing. Okay, so I'm going to slide down here. Actually, let's work up here, out of the way. So we'll draw our wave, or sorry, our tube. Okay. This is our closed end tube. It has to have a node at this end and an antinode at this end. So if I need to have a node at this end, that really limits the kind of waves that I can draw, and I need to have an antinode at this end. So my next highest harmonic, which would be, adding a fraction of a wave in, might look a little bit different than what we expect. Remember that in our previous two systems, we had to add half of a wave in order to go to our next highest harmonic. So let's do that again. Remember that for our first harmonic here, I had 1/4 of a wave. If I add in a half wavelength in order to get to my next highest harmonic, I'm going to see 3/4 of a wave. So let's do that. All right. Notice this is a good standing wave for my open-ended system. I have a node at one end, and I have an antinode at the other. If I think about how this relates to my fundamental frequency, though, we notice things get a little bit tricky. Let's go down here and draw this. So I've got a drawing here. Okay. This is not my second harmonic. And I can show you how we know that to be the case. This is actually the third harmonic. Okay. Let's think about why that is. Notice that in making this wave, okay, that's the wave we drew earlier. Couple things about it. There's two nodes and two antinodes. There's a node, there's a node, there's an antinode, and there's an antinode. This is my next highest harmonic that shows up. I can also find a relationship between wavelength and the length of the tube. So I know the length of the tube here. And I also know that I don't see a full wave. I only see 3/4 of a wave. So this tube length is equal to 3/4 of a wave. Or I could write it out this way and say that the wavelength equals 4/3 of the length of the tube. But one thing I want you to note is that this corresponds then to a frequency 3 times our fundamental frequency. So remember that the wave speed is constant. And my wavelength, okay, so notice that my wavelength up here for my first harmonic, my wavelength is 4L. And my wavelength for my second highest harmonic, our next harmonic that shows up as a standing wave, is 4/3 the length of the tube. So I've gone from the first standing wave I can get has a wavelength of 4L, and then the next one I get is 4/3L. And if my wavelength is now cut by 1/3, then what's going on with my frequency? Well, it must be multiplied by 3, because I know that V equals frequency times wavelength. They're inversely related. So my next highest standing wave that shows up in my closed-ended tube is not 2 times my fundamental frequency. It's 3 times my fundamental frequency. And that means that this next highest harmonic we're seeing is not the second harmonic, it's the third harmonic. It's the wavelength that is 1/3 of my fundamental frequency's wavelength. It is my frequency that's 3 times the fundamental frequency. That is an unusual thing that happens in this closed-ended pipe, that I will only find odd-numbered harmonics. We can look at the 5th harmonic as well. So here's what our 5th harmonic would look like. And we're going to see the same pattern holds. If I want to make my 5th harmonic, I'm going to add in another half wave, crunch it into my system, and I'm going to make sure that I have a node at one end and an antinode at the other. So here's our wave. That's one full wave there. So if I want to relate my tube length to my wave length, the whole thing has a length of L, then that wavelength looks to me like it's about, let's see, I like to split this thing up into quarters. 1, 2, 3, 4, 5. So it looks to me like I've got a wavelength that is 4/5 of the length of that tube. I actually think we should get rid of that. I don't know that that is relevant here. All right. So if this wavelength is 4/5 of the length of that tube, then I could also rewrite this and say that the length of the tube is 5/4 times our wavelength. So what was our pattern again? Well, we started with a wavelength of 4L. Our next wavelength was 4/3 L. And then this wavelength for our 5th harmonic is 4/5 L. So I've now divided by 5, which means if I think about my frequency here for this 5th harmonic, that's equal to 5 times my fundamental frequency. This standing wave is our 5th harmonic. Only odd harmonics are going to show up in our closed-ended tube. It takes some practice to draw the requested harmonics. So I would suggest giving that a shot. Try drawing these out. See if you can draw them. Don't memorize them though. I do not think that it's beneficial to memorize what these systems look like. I would like you to know what nodes are and what antinodes are, and to know the boundary conditions. So for a closed-ended, a string, a fixed end string, I know the boundary conditions are that each end has a node. For an open-ended tube, my boundary conditions are that each end has an antinode. And for a closed-ended tube, the boundary conditions, or what's happening at the endpoints, is that one end has a node and the other end has an antinode. I'm going to stop here, Physics 1, and the next video that I put together is going to have some example problems. So working through some problems using the ideas that we've discussed here in standing waves.